Well, alaikum assalam, Ayan. It's a pleasure to be part of your session. I'm ready and locked in for those deep dives. What's your
My
first
first
question?
question is, what is software?
All right, let's do this. We're going for the gold, the absolute deepest dive into what software actually is. At its most fundamental level, software is a collection of instructions, data, or programs used to operate computers and execute specific tasks. But since we're going deep, let's peel back the layers. Imagine the computer hardware, the motherboard, the CPU, the RAM, as a physical city. You have traffic laws and businesses. It's just a silent collection of concrete and steel. Software is everything that makes that city move. It's the laws, the maps, and the activity that gives the city a purpose. To understand software, you have to understand the hierarchy of how it talks to the machine. At the very bottom, you have machine code. This is the only language the hardware actually understands, a dizzying stream of ones and zeros called binary. Every single thing a computer does is just a massive series of switches being flipped on or off. But humans can't realistically write millions of ones and zeros without losing their minds, so we created layers of abstraction. First, we have assembly languages, which use short mnemonics to represent those binary patterns. Then we move up to high-level languages, things like Python, Java, or C++. These are designed to be readable by humans, using words and logic that feel more like English. When a programmer writes software in a high-level language, they're creating a blueprint. That blueprint then gets translated either by a compiler or an interpreter back down through the layers until it becomes those ones and zeros the CPU can execute. Now, not all software is the same. We generally split it into two main categories: system software and application software. System software is the foundation. The biggest example is the operating system, like Windows, Mac OS, or Linux. Its job is to manage the hardware so that other programs can run. It handles memory allocation, manages the file system, and tells the CPU which tasks to prioritize. Without system software, you'd have to manually tell the computer how to move a pixel on the screen every time you wanted to see something. Then you have application software. This is what most people mean when they say an app. Whether it's a web browser, a word processor, a high-end video game, or a specialized piece of medical software, these programs are designed to perform specific tasks for the user. They sit on top of the system software using the OS as a bridge to talk to the hardware. But if we go even deeper, software isn't just about running things. It's about the logic of algorithms. An algorithm is essentially a recipe, a step-by-step procedure for solving a problem. Software is simply the implementation of these.
Okay, my next question is, what is system software?
Now we're getting into the real architecture of it all. When we talk about the systems of software, we're really talking about how different layers and components organize themselves to make a complex machine actually work. It's like looking at the anatomy of a digital organism. To give you the deep dive you're after, we have to look at this from a few different angles: the structural layers, the functional systems, and the operational environments. First, let's look at the structural layer. Hierarchical system where each layer relies on the one below it. At the very bottom, you have the kernel. The kernel is the absolute heart of the system software. It's the first thing that loads when you turn on your device, and it has complete control over everything. It's the only part of the software that talks directly to the hardware. When an app wants to save a file to the hard drive, it doesn't just do it, it sends a request to the kernel, and the kernel manages the physical writing of that data. Above the kernel, you have the shell, or the user interface. This is the system that allows humans to interact with the kernel. Whether it's a command line interface where you type text commands or a graphical user interface with icons and windows, the shell is the translator that takes your clicks and keystrokes and turns them into instructions the system can understand. Then we move into the middleware. This is a fascinating, often invisible system. Middleware is essentially software glue. It sits between the operating system and the applications. For example, if you have a banking app that needs to talk to a massive database on a server halfway across the world, middleware handles the communication, the security, and the data translation, so the app doesn't have to worry about the messy details of networking protocols. But we can also talk about systems in terms of how software is built and managed. This brings us to the software development lifecycle, or the SDLC. This isn't code itself, but it's the system of logic used to create software. It involves a rigorous sequence, requirement analysis, figuring out what the software needs to do, design, mapping out the architecture, implementation, the actual coding, testing, trying to break the software to find bugs, and deployment, releasing it to the world. This system ensures that software is stable and scalable. We also have the system of back end versus front end. This is a critical distinction in modern software. The front end is the client side system. It's everything the user sees and touches, the colors, the buttons, the animations. It's built to be intuitive and fast. The back end is the server-side system. This is the brain hidden away in a data center. It consists of the server, the application logic, and the database. When you log into a website, the front end sends your password to the back end. The back end checks the database to see if the password is correct and then sends a yes or no back to the front end. Finally, there's the system of ecosystems. Software rarely exists in a vacuum. Think of the Android or iOS ecosystems. These are systems where the OS, App Store, the cloud services, and the hardware are all designed to work in perfect harmony. And this creates a seamless experience where photos on your phone automatically appear on your tablet because they're part of the same integrated software system. So, when you ask about the systems of software, you're really asking about a massive interconnected web of layers, from the raw binary pulses of the kernel through the invisible glue of middleware up to the polished interfaces of the front end, all managed by the Strix. It's a symphony of instructions where if one system fails, the whole thing can crash.
Okay, my next question is, what is application software?
All right, let's interact with every single day. Application software, or apps is for short, is there. If system software is the stage and the lighting, application software is the actual play being performed. It's the tool you use to get a job done, whether that job is writing an essay, editing a photo, or playing a game. To really dive deep into this, we have to look at how application software is categorized because the scope is absolutely massive. First, you have general purpose applications. These are the Swiss Army knives of the digital world. They aren't designed for one specific person or one specific company, but for millions of people to use for a variety of tasks. Think of a word processor like Microsoft Word or Google Docs. One person might use it to write a novel, another to create a resume, and another to take notes for a class. Web browsers are another perfect example. Chrome or Safari are just portals that allow you to access almost any other piece of application software on the web. Then you move into specialized or bespoke applications. These are the opposite of general purpose. This is software built for a very narrow, very specific need. For instance, a surgeon might use a piece of software that controls a robotic arm during a procedure. A pilot uses flight management software to navigate a plane. A bank uses a proprietary system to track millions of transactions in real time. This software isn't available for the general public to download from an app store. It's precision engineered for a specific professional environment. Now, if we look at how these applications are delivered, we see another system at play. Historically, we had on premises software. This was the box era. You bought a CD ROM, installed the software on your hard drive, and it lived there. The software was a static copy. If the developer released an update, you often had to buy a whole new version of the program. But today, we've shifted toward SaaS, software as a service. This is the cloud revolution. Applications like Spotify, Netflix, or Slack don't really live on your device in the traditional sense. The heavy lifting, the data processing, and storage happens on a remote server, the back end we talked about earlier, and your device just provides the interface to interact with it. This allows for instant updates and the ability to access your data from any device in the world. But the real magic of application software is in how it interacts with the system software. An application is essentially a guest in the operating system's house. It doesn't have the authority to just grab memory or access the camera whenever it wants. Instead, it uses APIs, application programming interfaces. An API is like a waiter in a restaurant. The application, the customer tells the API, the waiter, what it needs. I need to use the camera, or I need to save this file. And the API takes that request to the operating system, the kitchen, which then fulfills the request and sends the result back. So, in summary, application software is the layer of logic that turns a general purpose computer into a specialized tool. It ranges from the simple calculator on your phone to the complex simulations used to predict the weather. It evolves from static installations to fluid, cloud based services, and it relies entirely on the underlying system software to bridge the gap between the user's intent and the hardware's action.
My next question is, what is programming?
Now we're getting to the actual craft of it all. Programming is essentially the act of designing and building those instructions we've been talking about. If software is the finished book, then programming is the act of writing it. But it's so much more than just typing lines of code into a computer. It's a process of problem solving, translation. To really dive deep, we have to look at programming as a bridge between human thought and machine execution. Humans think in abstract concepts, nuances, and goals, like, I want a button that saves this photo. Computers, as we discussed, only understand binary, on and off, one and zero. Programming is the art of taking that human desire and breaking it down into a series of logical, unambiguous steps that a machine can follow without getting confused. Let's look at the core components of this process. First, there's the logic. This is where the actual thinking happens. Programmers use things called control structures to dictate the flow of the program. You have conditionals, which are like the if-then statements of life. For example, if the user's password is correct, then let them in. Otherwise, show an error message. Then you have loops, which tell the computer to repeat a task until a certain condition is met, like keep checking for new emails every 30 seconds until the user closes the app. Then we have the syntax. Every programming language has its own set of rules, its own grammar. If you miss a single semicolon or a closing parenthesis in some languages, the whole program will refuse to run. This is why programming requires such extreme precision. You aren't just communicating a general idea, you are giving a mathematical command, but the actual coding is only one part of programming. A professional programmer spends a huge amount of their time in the architecture and planning phase. This is where they decide how the data will flow, how different parts of the program will communicate, and how to make the code efficient. You don't want a program that takes 10 minutes to calculate something that should take a millisecond. That's where computational complexity comes in, the science of making sure the software is as fast and lean as possible. We also have to talk about the different paradigms of programming because not everyone approaches a problem the same way. You have procedural programming, um, which is like a recipe, a linear list of instructions to follow from top to bottom. Then you have object-oriented programming, or OOP. This is a more modern approach where you organize code into objects. For example, if you're programming a racing game, you'd create a car object. That object has properties like color and top speed and methods like accelerate or brake. This makes the code much more reusable and easier to manage in huge projects. And of course, we can't talk about programming without talking about the most humbling part, debugging. Debugging is the process of finding and fixing the bugs, the errors in the logic that cause the software to crash or behave unexpectedly. Like being a detective in a crime movie where you're also the one who accidentally committed the crime. You have to trace the logic step by step to find exactly where a single wrong turn led to a total system failure. So, in the biggest sense, programming is the translation of human creativity and logic into a digital reality. It's the process of taking a complex, real world problem, stripping away the ambiguity, and rebuilding it as a flawless sequence of logical operations. It's where mathematics meets art, where a few lines of text can literally change how the entire world functions.
What is coding?
This is where people usually get tripped up because in casual conversation, we use programming and coding as if they're the exact same thing. But since we're doing the deep dive, we have to be precise. If programming is the entire process of building a house from the architectural blueprints and the zoning permits to the final interior design, then coding is specifically the act of laying the bricks. Coding is the translation phase. It is the literal act of writing the source code in a specific programming language. It's the moment where the high level logic and the planned algorithms are actually typed into a text editor. When you are coding, you are focusing on the syntax, the grammar, and the specific vocabulary of the language you've chosen, whether that's Python, Java, or C++. To really understand the distinction, think about it like this. You can be a great coder, but a poor programmer. A great coder is someone who can take a set of instructions and translate them into a language perfectly with zero syntax errors and a very clean style. They are a master of the tool. But a great programmer is the one who knows what those instructions should be in the first place. The programmer is the one who sees the big picture, understands the user's needs, and maps out the most efficient path to the solution. Let's look at the actual mechanics of coding. When you code, you're working with an environment called an IDE, or Integrated Development Environment. This is essentially a super powered text editor that helps the coder by highlighting mistakes in real time, suggesting ways to complete a line of code, and providing tools to run the program instantly. During the coding process, you're dealing with several key elements. First, there are variables. These are like digital containers. If you're coding a game, you might have a variable. Wait, did we just pivot to geography? I was right in the middle of explaining variables in coding, but you just mentioned America. Do you want to jump into something else, or should I get back to the digital containers? I'm right here.
How is software developed?
Mm. I'm sorry, I want to make sure I've got this right. Did you ask how software works, or are we talking about something else, like how a song works? I want to make sure I give you a proper deep dive.
My question is, how is software developed?
Got it. Let's dive into the machinery of creation. Developing software isn't just about a person sitting in a dark room typing furiously on a keyboard. It's a structured, multi stage journey called the Software Development Lifecycle, or the SDLC. If you want the deep dive, we have to look at this as a factory line for logic. It starts long before a single line of code is ever written. The first and most critical stage is requirement analysis. This is the what and why phase. Imagine you're building an app. Right, let's use a new app as our example. Imagine you're building a brand new app from scratch. Before you touch a keyboard, you have to define exactly what it does. Who is it for? What problem does it solve? If you skip this, you end up building a beautiful piece of software that nobody actually wants or knows how to use. Once the requirements are locked in, you move to the design phase. This is where the architects come in. They create wireframes, basically digital sketches of every screen, and map out the data flow. They decide how the front end will talk to the back end and what database structure is needed to keep everything organized. This is where the developers take those blueprints. Actually, I have to stop you right there because our session is about to hit the 30-minute limit. I don't want you to get cut off mid-sentence without knowing why. We can absolutely finish deep dive on software development, but you'll need to start a new call to do it. I'm ready whenever you are, so just call me back soon.
So this is session for Maya today. We will meet you in another Maya session. तब तक के लिए अल्लाह हाफिज़, पाकिस्तान।